It is the physics video lecture, Physics 105B video lecture 6. And what are we talking about these days? We're talking about Lagrangian mechanics, another great topic today. In fact, we're moving into the discussion of conservation laws. So let me start with just reminding us what we have here in Lagrangian mechanics. And then work our way forward. So first of all, the equations of motion for a mechanical system come out of a variational principle. And they look like this. In fact, this, here, q sub I dot. This thing you see often enough looks just like Newton's law in my mind, yours too. Yeah, these q's here are the generalized coordinates. So I'll just write the set of q sub I generalized coordinates. Coordinates. Okay. And the Lagrangian. So generalized coordinates just give us the position of the system. They have to be independent. And then the Lagrangian is the difference between kinetic minus potential energy. Strictly speaking, this is between fixed boundary points. And because this is a scalar, and we have this principle, it doesn't matter what coordinates we choose. So as the systems become more complicated, the coordinate systems are more specialized, but one thing you're confident of is that this will give you, if you can construct this correctly, this will give you the correct equations of motion. Okay. So after this, I'll just number things the way we like to do. Last time we talked about constructing the Lagrangian. We had some examples. So constructing L, in particular, we had to get L in this form, Aij of Q, Qi dot, Qj dot minus Q of all the Q's. So this was the general form with this positive definite quadratic form for the kinetic energy. So this covers a lot of kinetic energies. There are Lagrangians that even go beyond this form. Possibly we'll see them later, but this covers quite a bit of ground here. So we construct L, and then, you know, equations of motion. Equations of motion are so complicated, we want to find some viewpoints. What makes it easier to solve a mechanical system, to understand a mechanical system, to solve the thing. And that's where we come into the conservation laws idea. So what I'm going to do is define something called, definition, something called a cyclic coordinate. The examples I give for this will turn out to be old friends, so to speak, stuff we already know. The cyclic coordinate, what is that? A cyclic coordinate is a coordinate that does not explicitly appear. So we have a Lagrangian, and in its most general form, Q1 to Qn, Q1 dot to Qn dot, and T. That's the most general form. A cyclic coordinate, let's say Q sub k, is when the kth, Q sub k, is not explicitly present. So what you typically have is you're missing the Q sub k, but you do have the q sub k dot. So q sub k is not explicitly present. How about if I not draw that arrow through there? Q sub k not explicitly present in the Lagrangian, but q sub k dot is present. And we'll see in a moment, we're very familiar with those scenarios, but I'm just giving you the definition now. A cyclic coordinate is not explicitly present in the Lagrangian. So now we've got this Lagrangian here with its cyclic coordinate, and example L equals L of Q2 to Qn, but it does have Q1 dot to Qn dot. Okay, so here Q sub 1 is cyclic. Here Q sub 1 is cyclic. Now, this is a really simple theorem actually. The equation of motion, so for K, we have d dx partial L partial, oh, we're using Q's, sorry, this is d over dt partial L partial Q K dot minus partial L partial Q K is equal to 0. That's the Euler-Lagrange equation. But Q sub k is cyclic, so for k being cyclic, let's get another color. Yeah, this must be identically 0. So k is cyclic, that's 0. The complete time derivative of dl dq k dot is equal to 0. Therefore, dl dq k dot is equal to a constant. And this dl dq k dot is referred to as a generalized momentum. I haven't brought that into play yet. This is a generalized momentum. Qk is a generalized coordinate, qk dot is a generalized velocity, dl dqk dot is a generalized momentum. And in this, under these circumstances, it's constant. Well, what does that mean? As we'll see in a moment, that means that we've just discovered a conserved quantity. So you can discover a conserved quantity just by looking at the Lagrangian. Again, this one here where Q1 is missing, immediately we could say P sub 1, the generalized momentum is conserved. Okay, so that's a huge and amazing feature of the Lagrangian mechanics actually. And that's the abstract form of it, and now I'll just show you the concrete examples that are very familiar. So the first example, let's do projectile motion. So for projectile motion, we have L half m x dot squared plus y dot squared plus z dot squared. Okay, that's the kinetic minus mgz, and x, y, z is my up direction. Z is my vertical direction, so there's the potential energy. So here, L is equal to L of z, x dot, y dot, z dot. It has two generalized coordinates that are missing. So it has two cyclic coordinates. L has two cyclic coordinates, namely x and y. So P sub x equals dl dx dot. Yeah, what is dl dx dot? Mx dot, okay? Mv sub x, that's the linear momentum in x component linear momentum. P sub y equals dl dy dot my dot are both constant. Both constant, double exclamation, okay? And we just have to write that out. Well, we don't even have to write it out because it's generally true, and of course we know that's true from projectile motion, right? Those horizontal components, horizontal velocities are constant, horizontal momenta are therefore also constant. This just comes out automatically in the Lagrangian. So if you see the Lagrangian like this, you immediately know that P sub x and P sub y are constants, conserved. So that, we'll write that down as a theorem or a statement. Namely, if you have generalized coordinate, if you have cyclic coordinates, you immediately have those corresponding conserved momenta. So we're numbering, aren't we still numbering 5? Let's number, we've got 6. And my statement number 7 is that generalized cyclic coordinates imply conserved momenta. Cyclic coordinates, conserved quantities. So here's another great one, and we had this on the board the other day as well. The Lagrangian for, so next, Lagrangian for the central force problem. Central force. So we remember the central force. Well, actually, let me write it down and then we'll discuss it. So L is a half m r dot squared r squared p dot squared minus u of r. So in the central force, we had a force F directed towards, in the reduced case, directed towards the origin, okay? And in plane polar coordinates, you just have u of r like that, okay? So we have, and by the way, we were able to reduce the problem from I'll just remind you, from 2 points in 3 space to an effective 1 particle in 3 space, and then we were able to reduce the motion in space to the motion in the plane, and that's when we introduced plane polar coordinates, which we also did without having Lagrangian mechanics, but we in fact used the energy. We had kinetic energy plus potential energy all the time, okay? So now the Lagrangian is just the difference of those. It is L of R phi R dot phi dot, but guess what? It does not explicitly have wrong, it doesn't explicitly have the phi. It jumped the gun on that. Here we go. It has the R, of course, it does not explicitly have the phi. So that's gone. And immediately we have P sub phi equals dl d phi dot. So that's the generalized momentum. Namely, it's just the corresponding momentum to the coordinate. That is constant. What is it? since we're differentiating with respect to phi dot, it's mr squared phi dot equals constant. Again, let's put some exclamation points there, because we just found a conserved quantity. Of course, we knew what it was originally. In order to put the plane polar coordinates in play, we had to know that the angular momentum is conserved. And this, in fact, is the angular momentum. Okay. But the point is that a Lagrangian of this form immediately has this quantity being conserved, and turns out to be the angular momentum in this case. So angular momentum. And this brings us to the topic of symmetries and conservation laws. I don't think I have to belabor this too much longer. If you have your cyclic coordinate, you automatically get this conserved quantity. There's some really fun exercises where you just define the Lagrangians pretty abstractly, and you just pick off the conserved quantities based on the cyclic coordinates. Maybe we'll do a couple of those. In fact, maybe we'll do one of those right now. So these are the ones we know. So here's what we'll do for another example, just to drive the point home. And this is also going to demonstrate that the choice of coordinates, that's the really important feature in mechanics in general, and Lagrangian mechanics makes that very explicit. If you can choose the right coordinate system, that's half the battle. In fact, in Physics 203 in graduate mechanics, we pursued a theory so far that you're trying to make all of your coordinates cyclic by clever transformations. And if all of your coordinates are cyclic, then all of your momenta are conserved. Okay, so all the work now goes into finding the cyclic coordinates. Okay, we won't do that in 105B. Got to save something. And let's just give some examples here to kind of drive the point home. We'll just call this find conserved quantities. Find the conserved quantities. Now here's the scenario. The first scenario is we have a picture of that. We have an infinite mass distribution along the z-axis. Infinite mass distribution. Along the z-axis. And we want to know what's conserved. So there's an infinite mass distribution. It's a linear mass distribution. It's got some finite radius. So you can imagine there's your z-axis. X, Y, Z, and Z direction, you have this infinite cylinder of mass. And now you want to know what's conserved. Well, the first thing you're going to do is use cylindrical coordinates. That just makes sense. So cylindrical coordinates. And now your Lagrangian is going to be 1/2 m for, your point particle here flying around. 1/2 m rho dot squared plus rho squared phi dot squared plus z dot squared. As you guys remember, cylindrical coordinates, rho, phi, and z. But the potential energy, what can the potential energy depend on? Okay, because we have this infinite distribution along the z-axis, it cannot depend on z, because anywhere you are in z direction, you're always just looking at the same situation. It's just a cylinder there, So it cannot depend on Z, nor can it depend on phi. Because if you're just, if you're at a certain distance from that cylinder and you change the angle, the cylinder still is exactly the same. This is called a symmetry. Okay. So all it can depend on is rho. It can only depend on rho. And if this were a gravitating cylinder, you would have one thing. If it were an electrostatic cylinder, you'd have another thing. But it can only depend on rho. And for that reason, we have the following. We have L equals L of rho phi Z rho dot d dot z dot. But what are the cyclic coordinates now? Phi and Z. And we immediately have two conserved quantities, P sub phi equals, I'll just write their definitions down. P sub phi dl d phi dot. We just essentially did that one. P sub z dl d z dot are conserved. Okay, so this brings us to the topic of symmetries and conservation laws. What I've just constructed here is something where there's a symmetry, namely that if I were to transform my coordinate system so that, or if I were to move in z direction, nothing changes physically. If I move in phi direction, nothing changes physically, okay? Yeah, so both of these are examples. And yeah, you may want to just calculate these out for practice, but we just did this one, angular momentum, and this will be linear momentum in the z direction. So this brings us to the topic of symmetries and conservation laws. We just talked about conservation laws a few days ago. This time in the Lagrangian formalism, you get a whole other view of them. Very nice. Okay. And basically, it's what's been shown here with the coordinates, with the cyclic coordinates, and that gets generalized one more step. Okay. So symmetries and conservation laws. Very important topic. Okay. This is something you'll have all throughout theoretical physics. Beyond this. Okay, let's see how we're doing time-wise. Good. So we'll start the symmetries and conservation laws section. And when we get through this, probably not today, probably next time, then we'll go back to solving some concrete problems. We have a bunch of topics in Lagrangian mechanics to cover. But good. So a cyclic coordinate expresses a symmetry in the mechanical system. And the cyclic coordinate is just one that's missing, and we have to generalize that a bit. Okay. Now the first conservation law we kind of already have, but I'm going to talk about it in this context. The symmetries are time and space. So symmetries of time and space. The discussion of all of these requires that we do our physics in an inertial system. So in an inertial system, first thing we have is that we say time is homogeneous. That means that every instant in time is just the same as the next instant in time. So time is flowing uniformly. So we say time is homogeneous. Now, in a non-inertial system, that's certainly not the case. If you're trying to do your physics on a bumpy road or in a car that's starting and stopping, okay, every instant is different than the next one. Okay, so you have to be in an inertial system moving with constant velocity, etc. Okay. So time is homogeneous, and that is expressed, or that expresses itself as our Lagrangian is not explicitly a function of time. Okay, that's an L. Lagrangian is not explicitly a function of time, and most of ours, have I erased them? Yeah. We aren't actually building many time-dependent Lagrangians, but we could. We could always have a time-dependent system. So in an inertial system, time is homogeneous, expressed by Lagrangian not being explicitly a function of time. And we had already found the conserved quantity for that. The conserved quantity for that we inherited from our variational calculus was the sum of dl dqk dot qk dot minus L is equal to a constant. But we didn't know what that conserved quantity meant yet. In the variational calculus, it was just the reduction of order of the differential equation, but what does it really mean? That's what we'll do next here. So now consider L being of this form with the double sum, the quadratic form aij of q, qi dot qj dot minus u of q, like that, I and j. So now what we have to do is take this derivative and then do this summation and subtract the original Lagrangian. So we got a little bit of work to do. So first, now dl dq sub k dot is 1/2. So we're only going to be working on this thing. There are no q dots right here. Working on the double sum. What we'll do is we'll go through the double sum. We can also go through aij of q, but we have to deal with these q dots. And what we have is delta q I k dot times qj dot plus qi dot delta q kj dot. So what have I done here? I've done a product rule, generalized here, and this is the Kronecker delta. So what this is saying is when I is equal to k, since k is what I'm differentiating with respect to, when I is equal to k, I get a 1 here. Oh, there's my mistake, sorry. That was looking funny, wasn't it? Delta I k q I dot. Okay. All right. Stranger things have been known to happen. And here we have the qj dot delta kj. Okay, once more with feeling. So Kronecker delta, when I is equal to k, or when k is equal to I, then I have a non-zero term, so that'll replace that with a k. And ditto for here. So remember, Kronecker delta ik is equal to 0, I is not equal to k, 1, I is equal to k. We do this calculation a few times in this semester, so let's carefully do this. So that means that you're summing over the i's and only one of them is non-zero. So what we get is 1/2. We've summed over all the i's, and only one of them is non-zero, and that's when I is equal to k, so we have a kj of q, and we had a qk dot qj dot, qk dot qj dot, okay. And on the second one, we're gonna go ahead and write the sum. So now only when k is equal to j, let's say only when j is equal to k, do we have a non-zero thing here. So now we're summing over the I, we've gotten rid of that, so we have a sub I k, right? Only when k was equal to j, so we have q sub I dot q sub k dot. Yeah, so that's one to play around with, okay? Now the next step here, oh well, making a lot of mistakes today, but we're catching them at least. When we take that partial derivative, we get rid of the one here that we were differentiating. So here, we got rid of this I here, replaced when it was equal to k, and here we got rid of the j1. So actually, kj, j dot, ik, I dot, okay. Do as I say, not as I do. Okay, yeah, I differentiated with respect to that q sub k dot, so I was getting rid of one of these, right? It was just linear in that expression there. So I was just left with one qj dot. Okay. Okay, that's what these Kronecker deltas meant. Sorry about that. Now, the next step is to note that, remember we said that these aij's were symmetric. And if they weren't symmetric originally, we were supposed to make them symmetric before moving on. So we can always make them symmetric. And that means we can call this the summation of a ki qi dot. This here is a kj qj dot. And since we're summing over I here and j there, these two sums are equivalent. Okay. And that means we can add them. So 1/2 plus 1/2 equals 1. And the result that we were looking for here is a kj qj dot j equals 1 to n. So, okay, I'm going to write this out and put a box around it. Okay, glad I caught that error. It's all one take, no edit. It's just the way it is. Okay, so now we're on our way to constructing this thing. Well on our way. Yeah, everything's up there that we need. Definitely recommend that everybody look over this very carefully, okay? Okay, so what's next? We're constructing this thing right above, so sum over k. The dl dq k dot, so we have the sum over k, and this thing is the sum over j. A kj q qj dot, and then qk dot, see? And now we're going to subtract off L, but subtracting off L is to subtract off 1/2 of our double sum, And you know what? I'll just do Kj, AKJ, QK dot, QJ dot. Those are just summation variable indices, no problem there. I'm subtracting off the kinetic and the potential. But this, you look closely, is identical to this except for the factor of a half. So I'm left with 1/2. So I'm left with 1/2 Kj, AKJ of Q, QK dot, QJ dot, and minus times minus is plus, plus U of Q. So what have we discovered? Our conserved quantity is the mechanical energy. So the energy conservation is a feature of Lagrangian mechanics where the time is not explicitly present in the Lagrangian. So a time-independent Lagrangian conserves energy, and that goes back to the symmetry of space and time. If you're in an inertial system and there's nothing out there affecting your system, you just have your system, it's isolated in measureless space, then energy is conserved. Okay, so we got conservation of energy out of this. Conversely, you know, if energy is not conserved, then you have some time dependence, so you have some outside influence. Okay, conservation of energy. So that's our first conservation law. Let's see how we're doing here time-wise. I'll just set the other or two up. I'll just discuss the other two a little bit, and we'll do their calculations next time. Okay. And we'll make this be enough of the board. Maybe I'll make up, you know what, I'll make up a homework problem too. So next time, space is homogeneous and space is isotropic. So homogeneity of space means that if you just move your experiment a little, this little sector of space is just as good as this one here. And isotropy, so space is isotropic, that means that if you point your experiment here, it's the same as if you pointed there. Okay, so space is independent of direction. Of course, only true in an inertial system. If you're on a turntable that's rotating, all bets are off, right? So, but if space is homogeneous and space is isotropic, we'll pick up the other important conservation laws. Okay, I have an idea for a simple homework problem that you're going to like. And that is the symmetry, just like we did the symmetry of the infinite mass distribution. Let's do another mass distribution and discuss what's conserved. So let's call this homework. Find conserved quantities. By the way, if the Lagrangian is time independent, doesn't have explicit t, then you can immediately say energy is conserved. So you know, I put that in your result. Find conserved quantities for this mass distribution. So here in measureless space, mass distribution. Did I even spell that right? Distribution. distribution. Okay, so we'll start in this Cartesian space, X, Y, and Z, and we're having some gravitating thing. It's some cosmically sized thing. It's a cosmic dumbbell. So there's a sphere here, and then down here there's another sphere. And this mass is gravitating. You know, we have a section on gravity coming up later in the semester, where we'll do this, you know. I'm not saying we're going to do this one, but we'll do gravity theory for mass distributions. Be that as it may, this one has a certain amount of symmetry to it. What are the conserved quantities and why? So find the conserved quantities for this mass distribution here. You're a little space capsule. There's gravity. Okay, you're a little satellite. You're trying to orbit this thing or what have you. What are the conserved quantities? And what you do is you find the coordinate system that you think is the right one and think over basically what the potential energy can depend on, right? Very similar to the one we did with the infinite mass, except it's no longer infinite. So anyway, there are interesting problems of this type, but we'll just do this one to add to our discussion. Give you a good chance to think a bit about these things. Cyclic coordinates and the like. Okay, I think that'll do it for today. This was the 6th video lecture, and see you all next time.